Hello, welcome general chemistry students and anyone else who's found this video on YouTube. I'm Dr. Ryan Hayes at Andrews University, Department of Chemistry and Biochemistry, and today we're going to learn a little bit more about electrolysis, specifically the quantitative aspects. We're going to do some calculations. Yay! More math. Love it. All right, first question to get us warmed up and going here. Water is oxidized to what at the what, leaving the solution what? What do you think? You can always pause the video and think about one of these answers and see if they make sense. Water oxidized to hydrogen and oxygen. It's one of those. It's just at the anode or cathode. It's one of those, and it's leaving the solution acidic or basic. It's one of those, and you picked, hopefully, oxygen is made at the anode, leaving the solution acidic. In fact, this is how a lot of electrolysis machines are made and used. People want to make acidic water. You can do it this way by electrolyzing water. Conversely, you can make hydrogen at the cathode and it will leave it basic or alkaline. Alkaline water, I guess people want that. Not in this video, we won't talk about that. OWL Lecture 58 homework is coming up due on Wednesday. There's not going to be anything else due. Today's lecture 59. We're going to finish electrolysis, part 2, quantitative aspects. I think it's actually really important to learn these two reactions that occur with water. I think it's kind of fun and easy. It's a good review on balancing electrochemical reactions. You should memorize these reactions that occur at the anode and at the cathode. There's two things that happen, but it's pretty easy to remember. Water is oxidized to oxygen. So make water the reactant, make oxygen the product, and we're going to balance it in acid. So I'll actually go through the steps. And then just remember the oxidation potential for that is negative 1.23 volts. So it's as easy as 1, 2, 3 to memorize. Get it? 1, 2. Okay, you got it. All right. And at the cathode, water is reduced to hydrogen. So oxidation at the anode makes oxygen. Reduction at the cathode makes hydrogen, and these are sort of the opposite things that happen. But we're going to balance this one in base. So it's the cathode that makes the alkaline. It makes some hydroxides in there. So let's look at the anode reaction. So if we have water that's going to make oxygen, we need to start balancing. Remember our rules. We balance with water first. So I'm going to put 2 waters on my reactant side now. And that gives me the 2 oxygens to balance with the two oxygens on the product side. Then next we come in with hydrogen. So I'm going to put 4 hydrogens on the product side. So I got my 4 hydrogens there. And then to balance those 4 plus charges, I need 4 electrons. There we go. I'm losing electrons. That's oxidation. And I just created the reaction that occurs at the anode. Go check it out. Negative 1.23 volts. A little bit harder at the cathode, but great practice. You need to do this. Water's reduced to hydrogen, so we better gain electrons. Put them on the reactant side, but follow the rules. Follow the rules. I'm going to balance an acid first. I always think this is easier. It's another step or two, but it's easy to handle. Okay, this is a bit weird. Stick with me. So look, I've got water going to hydrogen. So what's the step? What am I supposed to do? Balance oxygens. I got to put a water on the other side, but that doesn't make sense. They cancel each other out. Stick with me and do it. That's the rules. Okay, now I got 4 hydrogens on the product side. Okay, so I'm going to put 2 more hydrogens on the reactant side that give me the 4. And since I put a plus 2 charge, I need 2 electrons to balance it out. Okay, the charge is balanced on both sides. Hydrogens, oxygens, all balanced. Now the next step, we add hydroxides to get rid of the hydrogen ions, since I'm all balanced here. And so I'm going to add 2 hydroxides to both sides. Take those 2 hydroxides and 2 hydrogen ions on the reactant side, make them into waters. It gives me 3 altogether. Now I'm going to subtract off the water that I had to put on the product side. So I reduced to the simplest amount of water. And so I'm going to end up with 2 waters plus 2 electrons. Gaining electrons, that's reduction. Give me a hydrogen molecule and 2 hydroxides. There's the hydroxides that are produced at the cathode, and that is the cathode reaction. And remember, that's not oxidation, that is a reduction of negative 0.83 volts. Typo. I'll fix it in my notes. Time to go on. All right, what are some quantitative aspects of electrochemistry that we can use using some knowledge of amperage and current that flows through? So we learned in the last lecture that the voltage, if you have enough voltage, you can get a reaction to go. You can use electricity with a high enough voltage and you can turn on chemical reactions that are non-spontaneous. Gotta have electricity though. Where's that gonna come from? Batteries, great place. All right, let's say you've got silver ions reducing to silver metal. And what can we learn from this? Well, there's 1 mole of electron for every 1 mole of silver. Okay, that's nice. What if we could measure the amount of electrons that are flowing through? We could see that for every mole of electrons that we flow through the experiment, we can make 1 mole silver ions or silver metal. Same thing, right? Well, they're not the same thing, but they're connected. Everything's 1-to-1 in this particular half reaction. Because the half reaction sets the mole ratios. That's all we need to know. So we could, if we could measure the amount of electrons that are going through the experiment, we could calculate the number or the amount of silver that's formed. Aha, what can do that? How can we measure the amount of electrons? This is where amps come in. What's amp? It is current that flows through an experiment, and it's the amount of charges per time, or the number of coulombs per second. So I'm going to use coulombs and charge kind of, I'm going to use them the same way. So they're nothing new there. And C, they both start with C, so that's great. So amps equals current or coulombs per second. So that's how I remember it. A equals C over S. All right, so time is in seconds here. All right, so how is the charge related to the moles of electrons? Because we need to get this charge and electrons thing connected, and this is where Faraday's constant comes in. It makes this amazing connection for us. Faraday's constant is 9.6485 times 10 to the fourth coulombs per mole of electron. If those two, we've got a conversion factor here. It's all perfect now. So 96,485 coulombs per 1 mole of electron. If two things, if you got them in a fraction, they're equal to each other, it's just nothing but a big conversion factor for us. Okay, that's what a Faraday is. So let's use this in an actual problem here. Let's say you've got 1.5 amps flowing through a silver plus ion solution for 15 minutes. What mass of silver metal is deposited? All right, so here's how we're going to go through it. Got to get the coulombs here. Well, how do we get coulombs? It's trapped in that amperage formula. Amps is coulombs per second. Well, I'm told how many amps, and I'm told how much time. Got to convert the time into seconds, though. All right, so if we do that, then amps times seconds will give us the amount of coulombs. And sure enough, that's 1,350 coulombs that flowed through this experiment. All right, and now using the relationship, now that we know it's 1,350 coulombs, we can relate this now into electrons using Faraday's constant. How do we do that? Multiply by the conversion factor that's in Faraday's constant, and we can see how many moles of electrons that flowed. Okay, then perfect. Now that we got moles of electrons, we can then calculate using conversion factors, unit dimension analysis, and because of the 1-to-1 mole ratio stoichiometry in the silver half reaction, we can convert moles of electrons to moles of silver and then multiply by the molar mass of silver. Voila! And we can figure out the mass of silver. So 1.5 amps for 15 minutes, 1.5 grams of silver. It's not a whole lot, but I think we'd recognize if we can turn up the amps, we can let it go longer, more silver we'll be able to get more silver. Pure silver. Ha ha ha. That'd be great. All right, let's do one more calculation. The anode reaction in a lead storage battery is lead plus hydrogen sulfate ion to give us lead sulfate solid plus hydrogen ions plus 2 electrons. If a battery delivers 1.5 amps and you have 454 grams of lead, 1 pound, how long will this last? Well, that sounds like a really important question. Don't you want to know how long your battery will last? So this is a similar type of a calculation. All right, so how do we do this one? Well, we know how much mass we have. See, in the last problem, didn't know the mass. We were trying to get to that. So we're going to work this one backwards now. 454 grams of lead, we can turn that into 2.19 moles of lead. I should have done the math for you. Use molar mass. Go look that up on the periodic table. See if you get the same number of moles that I did. Okay, once you have the moles of lead, we can multiply by the half reaction that we have here in front of us that says 1 mole of lead gives us 2 moles of electrons. So now we know how many moles of electrons, 4.38 moles. So that's quite a few moles. All right. And then from the moles of electrons, we can work backwards here and go to coulombs by using Faraday's constant in kind of in the inverse way that we did before. So now we get 423,000 coulombs that flows through, or that we can flow or create or use in this battery that's got a pound of lead in there, flowing at 1.5 amps. Okay, so now we've got all this current here. What can we do with it? We want to figure out how much time. Well, we have time, we've got amps. No, we don't have time, but we have coulombs. We have coulombs and amps. And so we have 2 out of the 3 things in this formula, and we can solve for time. And the amps equals coulomb per time. So I rearranged it already for you. So to solve for time. So I plug in the charge, divide by the amps, and that gives me time in seconds. 282,000 seconds. Whew, seems like a lot of time, 7 to 8 hours. Not sure this is necessarily what's related to an actual battery, but you get the idea that if we know how much of one of the reagents is that's in the battery, the mass, we can convert it all the way back through using our half reaction. Didn't need to know all of it, and we can figure out how much time. So it all changes depending on the amp and the amount of material that's there. All right, so we've worked through a couple questions, and that's kind of it. You just need to go practice working with these problems. And so what have we learned about electrolysis here? Well, voltage sets the reaction that you can do. Kind of like this young lady, you get enough voltage, boom, you can make your hair stand up. And I'm sure that's what's happening when you do these electrolysis questions. All right, so 4 volts, if you have enough 4 volts, you could drive the electrolysis of water. Okay, you can do that. The voltage sets what you can do that gives you enough energy. So if you have a 9-volt battery, boom, you can oxidize, you have enough voltage there. Now though, how much oxygen and hydrogen can you make? That depends on the current. So it's the current that tells us how much we can make. And you may have heard it's not the voltage that kills you, it's the current. A lot of current flowing through the sockets. That's why we don't put anything metal, because that current is what drives the chemical reactions to do something dangerous. And so you do a lot of chemistry if you have lots of amps. So more amps, more power to do chemistry. So it's the amps that kill you, okay? So voltage then tells us what we can do, and the lowest voltage reactions go first. And then if once those things are used up, and then the next reactions go. So remember that current is amps equals coulombs divided by seconds. Remember Faraday's constant, 1 mole of electrons is 96,485 coulombs. And remember, you just need a half reaction. You don't need to have the balanced reaction there in order to do these calculations for electrolysis or a battery for time. And you just need time, mass, coulombs, you get these things. So remember, more amps, more coulombs, more cool chemistry. Thanks for joining me. And hopefully you appreciated this relatively short look at some problems dealing with the quantitative aspects of electrochemistry. So I'm Dr. Ryan Hayes, and signing out for electrochemistry and electrolysis.